the separation between thinking substance and extended substance, and the unique characteristics of the avatar, is an experience that you only get by practicing the ancient meditation practices, by practicing the hypnosis, by practicing one of these newer methods. It's an experience that you have. It's an insight. I mean, it happens in that flash of lightning that Heraclitus was talking about, that the Zen masters talked about. Okay? So, will not, I mean, the language that I'm using to describe it will make sense to you after you've had the experience. Until you've had the experience, it will only sort of guide you towards the experience. Once you've had it, everything that I have said here will make absolute, total sense. It will become clear, like everything becomes clear in that flash of lightning. Totally clear, absolute clarity, once you've had that experience. You can't have the experience, though, without doing one of these methods. We either have to go back and we either have to, do the Golden Dawn stuff, we have to practice meditation, we have to do hypnosis, we have to practice Descartes' meditative method of skeptical analysis, or we have to practice Husserl's method of phenomenological analysis. We have to actually go out and do it. And then it will happen. And it will happen when you're least expected. It will happen, when you're waiting in line, or when you're reading a book or something, it will just happen. Boom. And then all of this that I've said will make total, absolute, crystal clear sense. Because you'll know what we're talking about. You'll know what all of these people are talking about. And then you'll be able to enter into the dialogue. Up until the time that you have that experience, it is just sort of leading you towards that experience, sort of helping you understand what that experience will mean once you have it. So you have to go practice the meditation, you have to go practice the hypnosis, you have to practice the Cartesian skepticism or the phenomenological reduction. You have to practice those diligently. Then you'll have the experience. And then all of this will make total sense. And everything that they write will make total sense. You can go read them all and it will make sense because you'll understand what they're talking about. Okay? Without having the experience, though, it's difficult. It's just sort of pointing at it. Okay? There's an ancient Zen Koan. Basically, the master points to the reflection of the moon in the water. Okay? Because that's what the descriptions are. They're a reflection of the actual thing. Okay, so there's a difference between the description of the thing, in this case the difference between thinking substance and extended substance, and the actual thing, the experience of that. So keep that in mind. All of this will make sense once you've had that experience. And once you have that experience, you'll know it. It will just click. Okay, and at that point, there's another Zen saying, before this moment of enlightenment, mountains are mountains, grass is grass, things are normal. Right immediately after this, everything is topsy-turvy and nothing makes any sense because you're trying to figure out the implications of this for you personally in your own life. Okay, and then as you work out those implications and as it settles in and you begin to understand what it means that we are in fact thinking substances interacting through the extended world, interacting with the extended world through the avatar, then things resume their normal shape. Okay, minus one ingredient, minus fear. No longer fear of almost anything. Okay, it is the death of fear. Because at that point, you'll have the experience of your own immortality. And it will be something that, again, will be revealed in that flash of light. And it will be something that you don't have to worry about anymore because it's revealed to you. You'll now know it. Okay? So that's what all of this is all about. Everything that we've talked about up until now has been devoted towards that one goal, which is to provide you a description and a system for having that experience. So now you just have to go off and have that experience. Okay? Just keep in mind what it is that we're doing. All right, any questions or comments about Okay. Today we'll talk a little bit about the philosophy of physics, not in great detail because it's not totally that relevant, but I wanted to let you sort of have an idea of what this is all about, and I'll give you some ideas of people to take a look at, which will answer your question about, you know, perception and other things like that, how the brain works and everything else. Basically, philosophy of physics is a sort of a new philosophical endeavor, starting sort of with Descartes and moving forward. Physical cosmology is concerned with space-time, mass, the origin and fate of the universe. So those concepts that come from the ancients. Thermodynamics and statistical mechanics is concerned with energy, work, randomness, and information theory. Special and general relativity is concerned with space-time and gravity. Okay, and then we get to quantum mechanics, which is concerned with determinism, indeterminism, uncertainty, and complementarity. So these are modern physics. Modern physics has addressed all of these issues and has come up with some pretty interesting theories about all of them. It begins with Sir Isaac Newton, okay, who was contemporary with Descartes, Spinoza, Leibniz. He is the originator of classical mechanics, in which he describes the law of universal gravitation and the three universal laws of motion. So this is the beginning of the scientific revolution right here. Okay? Building, of course, upon Descartes, Leibniz, Spinoza, Aristotle, Plato, everybody else has gone before him. But now we're getting down to the math, we're getting down to the nitty-gritty. Okay? Now, he assumed that the laws apply to idealized bodies or objects with no reference to the observer. Okay? So he's not concerned with questions of metaphysics or questions of epistemology like Kant and Descartes were. All he's saying is, I am describing mathematically, I'm describing what goes on in the behavior and the relationships among and between these idealized bodies, whatever those bodies might be. Planets, people, billiard balls, whatever. Okay? So he's saying, I'm not going to get involved in the metaphysics of it. I'm just going to get involved in the description mathematically of this thing. Okay? So that's the beginning of science. Here's the law of universal gravitation. Okay? If two objects are being pulled together by the gravitational fields, okay, force 1 and force 2, force 1 equals force 2, and they both equal gravitational constants, okay, times the mass of the first object times the mass of the second object divided by the radius squared, the distance between the two centers squared. So he's now saying this mathematical principle applies to all objects in extended space, okay? Because he's now concerned with the relationships out there. Okay, so we've got a mathematical formula that he says is universal. The three laws of motion, this is where he talks about them in the Principia. So it's axiomata sive legis motus, axioms or laws of motion. The law of inertia, a body at rest tends to remain at rest, and a body in motion tends to remain in motion unless disturbed by some other outside force. Force equals mass times acceleration. The acceleration of a body is parallel and directly proportional to the force acting on the body and inversely proportional to the body's mass. So the more mass it is, the harder it is to push. But once it gets going, the harder it is to stop. Okay? So this one and this one are related too. And F2 equals minus F1. Every action produces an equal and opposite reaction. Okay? So he's saying these are the three laws of the motions of bodies. Basically. Now, so that's the Newtonian classical model of the way the universe operates. And of course, it's more complex than that. But we built an entire physics based on that, based on just those two primary concepts. The motion of the heavenly bodies, the motions of the planets around the sun, the motion of the stars, the motion of objects in space, the motions of objects on the planet. A major classical physics was built on just those simple observations of the relationships that obtain among all of the objects there. And that held from about 1700 to 1900. So about 200 years, we have a classical model of the universe that actually works. Okay? However, Max Planck, born in 1858 and died in 1947, He was the originator of quantum theory based on his work with Blackbody Radiation, and we'll look at that in just a second. He won the Nobel Prize in Physics for all of this work in 1918. Now, this will become important when we get to Dr. Eccles. Planck measurements. These are very critical that we understand that they are really, 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 really small. Okay? So the Planck's constant is 6.6, I'm rounding all of these out, times 10 to the minus 35th joule second. So we're 10 to the minus 35th. That's 0.0000035 zeros 1. So it's really small, teeny, very teeny, because we're now looking at the distances and at the interactions of subatomic particles. Very small. Okay? Instead of looking at the larger universe, we're now looking at the really teeny universe. Okay? The Planck mass is 2.2 times 10 to the minus 8th kilograms, so really small. Still small. Okay? The Planck time is 5.4 times 10 to the minus 44 seconds. Really fast. That's how fast things happen at the subatomic level. Okay? And the Planck length is 1.6 times 10 to the minus 35 meters. Again, very, very, very small measurements here. And he derived all of these from experimental computations, from experimental measurements and computations that yielded these results. And they have been, every year or every other year, all of the scientists pool all of their data and put it into this big computer, and it crunches the numbers and gets a little more precise number for all of these. Okay? So I've really rounded them up. They're very precise out to like, some of them are out to like 10 decimal places. Okay? So each year we get a little bit more precise with this stuff. So the only thing I want you to remember about this is that we're now looking at very small measurements, and that we are now beginning to take a look at the quantum reality, which is completely different than the reality that Newton described. So here's a blackbody radiation, the blackbody apparatus. Essentially, a blackbody is a graphite cube, because it holds heat really well, inside of which is like a filament, like in a light bulb. Okay? And it has a hole, very, 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 very teeny tiny hole that's drilled in one side. Okay, so that the radiation can escape. That's what it looks like. So that's a black body box. Now, Planck is doing work on this because he's doing the work in the late 1800s, 1894. He is commissioned by the Edison Company and some of the other companies in Europe to design a cheap, efficient electric light bulb. So there, I mean, you know, he's got money behind him to do all of this experimentation. He is only looking to try to find the best filaments and everything like that, based upon, you know, what his experiments will show, so that he can then go out and design this electric light bulb that they will then do. Of course, Edison beat him to it, and you know, through just simple trial and error over 2,000 different, you know, elements, objects, he finally found that the best thing that would work the best for the cheapest amount of money was tungsten. The best thing, the thing that actually was the most efficient, was human hair, but it didn't last very long. Okay, so anyway, that's why he's doing all of this stuff. Because he's doing all of this stuff, and because he's heavily funded, he discovered this following thing. The more energy I put into the filament, the color changes at the aperture, the hole in the box. So at 1,000 degrees it's red, at 2,000 degrees it's a little redder, orange, yellow, white at 6,000 degrees, blue at 10,000 degrees. Okay? And beyond that, of course, it's, you know, the ultraviolet, and below that it's in the infrared. Okay? So he just notices that happens. And here, you know, from left to right, we can actually take a look at it in the real world. If you start to heat a metal bar, you can see that the hotter it gets, the color changes. And it will move all the way through that until it's blue, white, hot, and then it begins to melt. Okay? Now, nothing is really exciting about this except for the fact that he wants to create this curve. He wants to say what this curve would be. Because he wants to find the exact point where, you know, you get the right amount of energy for the right amount of light. That's what he's looking for, is that perfect place on this curve where you have more and more energy put into the curve, and more light put out until you reach exactly that spot where this is going to operate perfectly and effectively and efficiently. And he thinks, because he has been taught classical mechanics, he thinks that this is going to be a solid curve. That the more energy I put in, I can turn it up just a teeny bit and it goes up a little bit. But his measurements don't follow that pattern. They are discontinuous. He turns it up a little and nothing happens. He turns it up a little and nothing happens. He turns it up a little more, nothing happens. A little more, boom, it moves to that next level. He turns it up a little more, nothing happens. More, until finally it moves to the next level. And he's saying, this is odd. This is really weird. I didn't expect that. But he plots the graph. He plots the curve. And he finally gets a really good curve based on a lot of measurements. And in order to explain this curve, he has to assume that the element, that the energy itself is contained in these discrete little units called quanta. That it's not a continuous thing, that it's elements, that it's discrete little units. Okay? Now he thinks he's just, that this is something he'll be able to discard later on. He has to introduce this idea in order to make the data fit the facts. But he thinks it's just a fiction that he is now using in order to explain what's going on and to make the equations work. Okay? Albert Einstein, however, here's Planck's law. You can see it's discrete. Okay? All the way along, all the way up to the entire range. It is discrete units. Okay? And again, keep in mind, he thinks this is just an anomaly. He doesn't place any real credence to it at all because it violates classical mechanics, which says this should be a continuous phenomenon without any discrete steps at all. Now, Albert Einstein, born 1879, died 1955, of course the originator of special and general theories of relativity, which we'll get to in a second. But he just demonstrated the wave-particle duality of electromagnetic radiation by the photoelectric effect based on the blackbody radiation experiments done by Planck. Because Einstein sees what this means, where Planck didn't originally. He finally does. He finally, after Einstein explains it to him, he finally understands exactly what he's discovered. Okay? Also, of course, E equals mc squared, that most famous. All based on that same thing, all based on Planck's work. Won the Nobel Prize for Physics in 1921 for his work on the photoelectric effect, not for his work on relativity. Okay? A good book about relativity is this book by him, specifically written for a non-specialist audience. You can actually go get the original papers, and it's really, really hard to understand. But this is easy. He specifically wrote this for us to understand relativity. Okay? So, just to show, remember that light was considered to be a wave phenomenon. You can see it because it's, the only reason it can be distorted and split into its component spectrum is because it is a wave phenomenon. All right? It can be reflected and it can be refracted because it's a wave phenomenon. It's waves. And waves behave like this. Okay? They can be bent around corners, which is what's happening here. All right? And the reason why this happens is because these frequencies are slow, so the bending is less. These frequencies are high, so the bending is more. It comes through there and it bends more because it's going faster. The wave, the frequency is high frequency. Okay? Wave phenomenon, which is exactly what the thermal properties should have been. It should have been a wave phenomenon because this is infrared radiation. This is heat. It should have been a solid curve in the blackbody radiation experiments, but it wasn't. Okay? Should have been just like that. Here's the photoelectric effect. This is where Einstein gets his idea that then leans back, he then goes back to the blackbody radiation and understands what's going on. Incoming light waves on the left, in red, strike a metal plate, a specific metal plate, silicon and whatever, piezoelectric crystals, I can't remember. The electrons in blue are ejected by the collision and are seen moving off to the, to the right. Off to the right here. So we have this wave phenomenon, the light, coming in and striking the solid object, and what we get is electrons. You put light on this thing, you get an electrical current out. And this is what is going on here. The wave phenomena come in and hit the individual electrons and push them along. Okay? Wave phenomena can't do that. Only particle phenomena can do that, like billiard balls. All right? So Einstein thinks, wow. He's writing this paper in 1905. He thinks this is exactly what Planck demonstrated with the Blackbody radiation. The same thing, discrete energy units. All right? And so this is the beginning of quantum physics, which is the physics of very small objects. Okay? And it is nothing at all like the large universe that, like the mid-range universe that the classical physicists were describing. Special relativity is talking about the larger, bigger universe. Here, the implications of the postulates of relativity. First, time and distance will be measured differently in different inertial frames. So depending upon the relative speeds of the two objects, you'll get different results. So relativity means literally that. We have to put the observer here, and not necessarily the observer's frame of reference, we have to say, and the object's frame of reference, because if there are differences in speed that are great enough, it will begin to distort what we actually experience. Okay? Time will be dilated and lengths are contracted. When, this is the Lorentz equation. This is one of Einstein's predecessors, Lorentz. Okay? At velocity 0.42 the speed of light. So at 0.42% the speed of light, which is going to be, what would that be? Just a second. Anybody remember how fast light travels? 186,282 miles per second times 0.42. So at 78,238 miles per second, okay, gamma becomes 1.10. All right, so you can see what I don't know if you remember your math. But what this does is turns this into an imaginary number, okay? Which means the effects of relativity become noticeable at 0.42 the speed of light, 78,000 miles per second. If we could accelerate something that fast, and we can, then we get length contraction and time dilation. Time slows down and length shortens. Okay? Now, we cannot move large objects. Well, we might be. Well, we can move small particles that fast. That's what the electron proton. That's what, like the CERN particle accelerator is doing over in Switzerland, speeding up these objects to near the speed of light and then running them into each other. So we've tested all of this stuff and we know that it is actually accurate. Here's a Calvin and Hobbes. It disturbs me that this wagon has no seatbelts and wouldn't survive a 30-mile-per-hour impact with a stationary object. Why do you bring this up? Oh, no reason. Okay, so Calvin asks Hobbes, want to help me test the theory of relativity? Sure, the idea is that the faster we go, the slower time goes. Gotcha, it's now 10:23. What time is it now? It's 10:24, go faster. We're going pretty fast. What time is 10:25? Time still hasn't stopped. Has time stopped now? No, just my heart. Well, it looks like Einstein's a fraud, wouldn't you say? No, he's right. Look at my watch. It isn't going at all anymore. Okay. General relativity is the theory of gravity. And basically what Einstein discovered was that if space-time is a manifold, massive objects begin to warp the very fabric of that manifold. And so that's why we get gravity. That's why we get gravitational effects. It's not a force per se. What happens is it distorts space-time. The Earth here distorts space-time, creating this gravity well. So anything that comes into it will be pulled towards the center. Okay? So it's a function of space-time, and it's not a force per se. Okay? Is that a crack in Einstein's theory of relativity here? Nothing's perfect. Okay, there are some cracks in it, but very few. That has been tested as well. Heisenberg, born in 1901, died in 1976. He was one of the originators of quantum mechanics, and his most famous postulate was the uncertainty principle. Okay? That there is a fundamental limit to the precision with which certain pairs of physical properties of a particle, such as position and momentum, can be known simultaneously. because we're not dealing with really tiny things. And so there's a lot of uncertainty here. Remember what Hume said. Okay? Nothing we can know about that stuff out there will ever be perfectly certain. It will only be probabilistic. That's what the uncertainty principle says. There are limits to the precision with which we can know anything at that level. Okay? He won the Nobel Prize for Physics in 1932 for this work. So here basically is a diagram of the uncertainty principle. He used this to teach his students. He said, imagine a microscope that we could look at an electron with. So here's the microscope here. Here's the electron. And we're going to perturb the electron's motion with this light wave over here. Okay? So what's going to happen is, this thing is going to move left and right, the change in direction of X here. Now this thing is going to be reflected into the microscope, which is how we know anything, because the light wave reflecting off of it, we see, and that's what gives us the information about the movement of the particle. Okay? So, gamma ray microscope here. The photon is in green, the gamma ray is in green, the electron is in blue, the reflected photon is red. If the photon has a short wavelength, and therefore has a large momentum, like a gamma ray, it's very fast, very high, very dangerous. X-rays, then gamma rays. So very fast. Position can be determined, but momentum is uncertain, because it'll reflect off of that, and we'll see where it was, but we will not know where it is now, or how fast it's moving. Because that information cannot be given to us. If the photon has a long wavelength, low momentum, then we will know its momentum, but not its position. Okay, simply because we're dealing with two small things here. There's too small. The interactions of these things disturb the actual, nature of what they're doing. So we can only know a little bit about it, and most of it is probabilistic. Okay, Niels Bohr, again, a contemporary of all these people, another originator of quantum mechanics, the Nobel Prize for Physics in 1922. He developed a planetary model of the atom. Remember, that's the one we learned earlier. The nucleus here, and then all of the electrons in orbits. Okay? And what he said was that the orbits, as they move further out, are higher energy orbits. Okay? Which explains the blackbody radiation, why it is discrete. So what you have is you have distinct orbits, according to Bohr, the Bohr model. You have distinct orbits, and there are 8, well, more if you have bigger, heavier elements. But there are 8 of which can account for all 92 natural elements. Okay? So you have the inner, and then there are 7 others. The nucleus, the first shell, the orbital shell, and then all the way out to the 8th one. So plutonium would have this 8th shell filled. So it not only explains, blackbody radiation, but it also explains the periodic table of the elements and why everything falls in that particular pattern. Okay, as you move across, you keep adding electron to the orbits. Okay, so hydrogen is up here with 1 electron. Helium is over here with 2 electrons, and that fills up the inner shell. Then you have to move to the next level. So now you're working at the next level, the next orbit, the second orbit. So it's going to have the 2 electrons in the first orbit and the first electron filled in the second orbit. And then the 2 electrons, 3 electrons in the second orbit, so on. Okay? Remember that from chemistry? Okay, so that's what he's talking about. Atomic Physics and Human Knowledge was a book that he specifically wrote talking about the philosophy that emerges from, quantum mechanics and its kind of strange way of seeing things. Here are some additional people. I'm just going to blaze through them. You can go take a look at them later. Manly Palmer Hall was 1901 to 1990. He founded the Philosophical Research Society in 1934. And he authored 150 books and gave 8,000 lectures on philosophy, mysticism, and science. Okay, one of the lectures that he gave is this one here, The Atom in Religion and Philosophy, where he talks about not only the moral implications of nuclear energy, but also, some of the relationships between ancient Greek philosophy, Buddhist philosophy, Hindu philosophy, and the theories, quantum theories, atomic theories. Okay? Henry Margenau died in 1997. He was a professor of physics and natural philosophy at Yale most of his life, all of his career mostly. He was a staff member of the Institute for Advanced Study, which is where Einstein was. staff member of the MIT Radiation Laboratory too. So he's an actual working physicist. Okay, so his books are really good. Okay, here's one. This is The Miracle of Existence. Here's another, Einstein, Space, and Van Gogh's Sky. So he knows what he's talking about. Okay, and one very important book here. This is The Nature of Physical Reality, 1950. This is the first book for the non-specialist about quantum physics, 1950, and he was the one who wrote it. So basically, it was a textbook for his students. Really good stuff. Okay, because he knows what he's talking about. So The Nature of Physical Reality, Open Vistas is another one, 1961, Einstein, Space, and the Miracle of Existence. So you can get really good understanding about quantum physics and the philosophy that entails. Okay? Friedrich Capra wrote this book, The Dao Physics. He was a theoretical physicist, okay, actual practitioner as well. This is called The Dao Physics, an exploration of the parallel between modern physics and Eastern mysticism. So here he says Eastern metaphysics and modern quantum physics are both pointing to the same reality. And he draws those parallels here. The book is actually pretty well written. Okay? My only criticism is that he's not a mystic. He doesn't practice the meditation and those other things. So his descriptions of that are a little bit off. But it doesn't matter because it's still a good book. It's still well worth reading. Okay, Gary Zhukov is still alive. Born in 1942. He looks sort of like President Bush. He is a best-selling author. You know, he's appeared on more than 30 times on the Oprah Winfrey Show since 1998. He's the author of The Dancing Woolly Masters, an overview of the new physics in 1979. Okay? I like the book. It's pretty easy to get through. He's a lightweight, however. If you really want to understand his stuff, go to Marginal. Go to Marginal's books. Don't go to Woolley. Don't go to him. Again, he's a popularizer of this stuff. But, again, it's kind of, you know, it's easier to read. But it's not as in-depth. And again, he doesn't practice the meditation, so his descriptions are lacking there as well. Ken Wilber is even worse, but he at least includes sources from the original quantum physicists. Quantum Questions, Mystical Writings of the World's Greatest Physicists. Now, his interpretations are inaccurate, I would say. If you want to know what they really said, go read their original works. But this will give you an idea of who they were and where they fit in the pattern. Okay, so again, he's a popularizer. If you want the real stuff, go to the real people. Don't go to these guys. Okay, any questions about that? I bring that in only because it always comes up. Quantum philosophy and quantum mechanics, like I said, ever since the Dao Physics in 1975, every hippie on the planet thinks that they understand things, okay? Even though they don't practice it, even though they don't actually go back to the original sources and everything else. Okay, so quantum mechanics always comes into discussions. And it should, because it's real and it's valuable and it points in the right direction. Okay? But we have to get into it. We have to actually look at it seriously. Now we're going to take a look at the difference between materialist neuroscience and the dualist-interactionist neuroscience from Dr. Eccles that I particularly like. Okay? I also like the materialist neuroscience as well. Basically, their claim is that consciousness is an epiphenomenon of the activity of the brain. Okay? The brain stops, consciousness stops. Okay? So all it is just the brain working. That's basically what the materialists are talking about. So here is where you will find the answer to your questions about perception and how the nervous system operates. Okay? Douglas Richard Hofstadter. Here's some of his books. Metamagical Themas, The Mind's Eye. This is Fluid Concepts and Creative Analogies. That's a good one. And then he's got this really, really, really thin little thing. Okay? This is called The Tumult of Inner Voices, or What is the Meaning of the Word I? Okay? Now, he is a professor, he's the son of physicist Robert Hofstadter, who won the Nobel Prize in Physics in 1961. So his dad was a genius, he's a genius, he really writes well, he's got a lot of good sources. I really like him, even though I don't agree with his conclusions. I really like him because he's good, he's tight, okay? He is currently a professor of cognitive science at Indiana University in Bloomington, Indiana. his basic premise is that consciousness is an emergent property of the low-level activity of the brain. Okay, the brain does its thing, and voila, consciousness emerges. It's not this separate soul out here that we are. It's not immortal. It's just an epiphenomenon, this byproduct of the operation of the nervous system. That's what he argues. Okay? There are 4 books that are really good. Gödel, Escher, and Bach, and Eternal Golden Braid. Gödel, Escher, Bach. This one is kind of fun to play with. A Metaphorical Fugue on Minds and Machines in the Spirit of Lewis Carroll. Okay, now this one, he makes some predictions about artificial intelligence, which he was wrong about because they've actually gone further. The Mind's Eye, Fantasies and Reflections on Self and Soul. He wrote this with Daniel Dennett, which we'll take a look at in just a second. Okay, again, keep in mind they do not believe there is such a thing as a soul. They're total materialists, total determinists, absolute atheists. Okay, the Tumult of Inner Voices was the one I just talked about. Metamagical Themas, questing for the essence of mind and pattern. Fluid concepts and creative analogies. Computer models of the fundamental mechanisms of thought. So he's talking about artificial intelligence and computer models. If consciousness is a result of the activity of the neurons in the brain, then if we can make an artificial intelligent device that has the same properties, that machine will have consciousness. That's his basic premise.
Sorry, that's the funeral.
No problem. Oh, okay. Well, all right.
See you next time.
We'll see you next time. We'll catch up on all this. Okay, Daniel Dennett. He's still alive too. Professor of Cognitive Studies at Tufts University in Medford, Massachusetts, just right outside Boston. He is a strict determinist and atheist. He's a proponent of neurodarwinism, the position that evolution can account for all neural functions, including consciousness. Okay? So we're nothing more than a meat sack that happens to have this strange epiphenomenon that doesn't have any real value, except evolutionarily speaking. So somewhere along the line, in evolution's long chain of events, it was necessary for the survival of the species that we evolve a nervous system that would be conscious so that we could then dominate the planet, basically, is his idea. Okay? Which,
is a determinist, is that an atheist?
no, a determinist is someone who believes that the universe is determined by physical laws. So if you know, Newton was a determinist. All of classical mechanics is deterministic. Basically, if I know the position of any particle at any time, I can basically calculate the position of every other particle in the known universe from that one single datum.
Oh.
Because everything is determined, following specific, concrete, valid, verifiable laws that are inviolate. So it's all determined.
Oh.
Okay? So he's a determinist and an atheist. He believes that everything that happens is determined. No free will. The free will is an illusion, according to them.
Oh.
All right? Consciousness is mostly an illusion. Okay? It's not the thing that we think it is. It's not this immortal soul that is interacting with this avatar, okay, and experiencing the world out there. It is just the product of the nervous system as it goes through its normal daily routine, basically. Okay? Here's a couple of his books, Consciousness Explained and Kinds of Minds Towards an Understanding of Consciousness. I really like this. Okay? All right, I really like the title, Consciousness Explained. Okay, it's over with, it's done. No one ever has to question what consciousness is ever again, because Dr. Dennett has told us exactly what it is. But notice, it obviously wasn't explained well enough because he had to put out another book 5 years later.
So does he say that there's no subconscious?
Yeah, none of that. All of that can be explained simply by processes in the brain. Okay, there's none of this. All of that stuff are just fictions that are maybe useful for certain psychiatrists operating in a certain model, but they're not real. Okay, and everything is strictly determined, and everything is a consequence of the actual physical structures of the neurological systems. That's it. That's all there is. Nothing else. Okay. Yeah, no subconscious, no unconscious, no consciousness as we are thinking about it at all. Okay, again, I do like Dennett. He's good. He's very well read, copious footnotes, lots of bibliographical references. He writes extremely well. He's easy to follow. Okay, I just think he's wrong. okay? But you learn a lot from him, a whole bunch. Patricia Smith Churchland, this book here. Oh, which is the one that she wanted to know about. Yeah. Here we are. This is neurophilosophy, okay? She's still alive. She's emeritus professor of philosophy at the University of California at San Diego. She is the wife of philosopher Paul Churchland, and they together write many books and articles and go around talking about this, giving lectures. She was mentored by Francis Crick, the co-discoverer of the DNA structure. Okay? She also is a strict determinist, physicalist atheist. This is her book, Neurophilosophy, okay? Toward a unified science of the mind-brain. Again, she's making a claim that everything we experience is just a result of the operation of the nervous system itself. In here are all of the descriptions about how the nervous system operates and how it, according to them, produces all of our experiences. Okay? So that's that book there. You get a lot of information. Again, very well written, very well researched, good illustrations. She writes really well. We can learn a lot from her. Okay? Francis Harry Compton Crick. He died in 2004, co-discoverer of the structure of the DNA molecule in 1953 with James Watson. Nobel Prize for Physiology or Medicine in 1962. Strict determinist, strict evolutionist, strict atheist. Proponent of the concept of directed panspermia. Namely, that life on this planet was seeded deliberately by some extraterrestrial agents. Okay? If you saw the movie Prometheus this last summer, that is panspermia. Some alien, basically seeded us here, and that's what's going on. Okay, he's also a eugenicist. Okay, Of Molecules and Men was one of his earlier books, pretty accessible, and The Astonishing Hypothesis: The Scientific Search for the Soul, 1994, fairly recent. Okay, John Roger Searle, professor of philosophy at the University of California, Berkeley. He's a critic of Dennett and Crick and Churchland and all of these other people. He's a proponent of biological naturalism, that consciousness is a real subjective experience created by the activity of the brain. In other words, they're saying consciousness isn't really there, it's only apparently there. Consciousness really doesn't exist, it's just this, doesn't really exist, okay? He's saying, yeah, it does exist, but it's still only a product of the operation of the brain. We do have these experiences of subjective reality, and they're real, but they're only caused by the brain itself. There's no soul. There's no anything beyond that. It's still, flatly materialistic. Okay? This implies that AI is possible as well. So he's a follower of Hofstadter because, if we can create a machine that has the properties of the nervous system, voila, we'll have a thinking machine. Okay? So he's sort of midway between it. He wants to say, yeah, all those subjective experiences you have and everything that everybody else has been talking about are real experiences, but they're just byproducts of the nervous system itself. Okay? Rediscovery of Mind and the Mystery of Consciousness are two books where he describes this. Dualist-Interactionism. Consciousness is independent of the neurological structures of the brain. Okay? Hopper. Two things we have to remember about him: consciousness is ignored or completely, doesn't exist, cannot explain their own accident. Okay? What is it about the nature of reality that makes Daniel Dennett sit down and write a copious volume called Consciousness Explained? If it's not free will, and if he doesn't have a consciousness, how the hell did he even write the book? Okay? What set of deterministic principles, what set of deterministic properties, just happen to coincide at exactly the right nanosecond that set in motion that long process? Okay, so that's one of the challenges that they can't explain. Okay, and then of course the famous one, the most difficult one that they have, is the binding problem. Consciousness is a synthetic totality. Okay, all of that is synthesized into a single experience. No structure in the brain can account for this synthesis. It is not the microstructures of the brain that are providing the experience of consciousness. There is no, universal collator in the brain anywhere that collates all of the data, the visual data, the kinesthetic data, the sound data, the auditory data, the kinesthetic data, and puts it all together into this experience. Nowhere in the brain does that function exist. It just doesn't. Okay? So when Hofstadter says it's just all of these things going on at the neuron level, and that yields consciousness, that's obviously patently false, because there's no way to get from that microstructure of nervous activity to a synthetic totality of consciousness. Absolutely no way. And that's the binding problem. So they've got two problems. Number one, the problem of, they don't have a consciousness. How did they write the books? And the binding problem. They cannot explain consciousness itself as a synthetic totality from the microfunctions of the brain. Okay, does everybody have to go? Okay, we'll pick up this next week. I'll just finish with this because we're almost done. So I'll pick up that next week because the next thing is the most important thing, and we'll tie it all together with Dr. John Eccles next week. Okay, see ya. Any?
That was a fast class.
Yeah. All right.
Thank you.
You're welcome. See you next week.
Okay.
Yeah.